Alright, let's represent the following using interval notation. So for part A, we have x is greater than negative 2 and less than or equal to 5. So I'm going to write this as, x belongs to, if it's greater than negative 2 is not inclusive of negative 2, use the round brackets, negative 2, lower limit. And in this case, the upper limit, x is less than or equal to 5. So I'm going to use the square bracket because it is inclusive of 5. Okay, so that is an interval notation. Now let's take a look at part B. Right, so when we want to represent the following using interval notation. Think this portion here, they're basically referring to this interval here. Okay, so if they're referring to this interval here, what we want to do here is we want to look at all of the values that's greater than negative 3 but less than or equal to 3. So x belongs to greater than negative 3, which does not include negative 3, so we use the round bracket, comma, less than or equal to 3. And we're going to use the square bracket for less than or equal to. Okay. Part C here, we have two intervals that we're looking at. We're looking at negative infinity to negative 4, as well as everything greater than 1. Right? You can see that it's inclusive of negative 4, but it's not inclusive of 1. So for one of my intervals, we have x belongs to. Now for negative infinity, you cannot include negative infinity within an interval because it's not an actual finite number, right? Infinity is a continuum. Negative and positive infinity represent two ends of that continuum. So x belongs to negative infinity, lower bracket, we're going to use the round brackets, comma, and because it's inclusive of negative 4, we're going to use the square bracket. Now the other interval that x belongs to here is basically x is greater than 1, right? So because x is greater than 1, it's not inclusive of 1. So 1, we use the round brackets, and this is going to go all the way to positive infinity. And once again, positive infinity is a continuum, so we're not going to address it with the square bracket. Now because x will belong in both of these intervals, we want to say it can exist in the interval between negative infinity and negative 4, as well as 1 and positive infinity. So we use this union symbol, so this means union, or just it's a really fancy way of saying or. Okay. Let's take a look at part D here. X is greater or equal to negative 5 but less than 7. If we want to draw this out, and we want to represent this in interval notation, x belongs to negative 5. Okay, we're using the square bracket because it's inclusive of negative 5 and less than 7. Okay, so if we did draw this out, I'm not going to draw this to scale, but in this case, this point here would be negative 5, and this would be 7. Right, this would be positive infinity. You can see that I'm basically addressing all of this. Okay, so it's everything within this interval, and basically it's not inclusive of 7. Let's take a look at part E. So here we have x is less than negative 2, which is not inclusive of negative 2, but x is greater or equal to 4, right? So let's write x is less than negative 2 first, right? So we're doing negative infinity all the way to negative 2. We're using round brackets. Then we're going to do union, or x is greater or equal to 4. Now, because it's greater or equal to, it's inclusive of 4, we're going to use the square bracket. And then we're going to follow this off with the positive infinity with the round bracket. Okay, and those are our, that's how we use interval notation using the function method. Alright, let's solve the following inequality. Negative 2 times x plus 4 times x minus 3 times x minus 2 squared is less than 0. Okay, so if we're trying to solve an inequality, let's first determine the critical points. And the critical points include x-intercepts, discontinuities, any kind of extrema. And really what we use the critical points for are basically to determine our intervals. Now in this case, I'm going to look at my x-intercepts. So the x-intercepts can be determined when you set this expression to equal 0. I'm going to call this expression f of x. Right? If I let f of x equal 0, you can imagine that if any of these factors equal 0, 0 times the other factor will give you 0. So I'm going to let each factor equal 0. So I'm going to let x plus 4 equal 0. So if x is equal to negative 4, then you have an x-intercept. And you can do that for each of the other factors. X minus 3 is equal to 0, x is equal to 3, and also x will be equal to 2, right? So those are our x-intercepts. And after we have our x-intercepts, which include -4, 2, and 3, what you want to do here is design a number line to determine the intervals. So the critical points are used to determine intervals, and the space between the critical points is basically an interval. Now I'm going to show you that using a number line. So I'm going to just do that here. Okay, and let's say that this is 0. And because we're looking at values that are less than 0, this means that they are not inclusive of 0. So we're going to basically use non-inclusive points. So I'm going to use a non-colored in circle here. So this is -4. So it's not going to include -4 because then the whole expression itself will be equal to 0. This is -4. This is -infinity. This is like 0. This is 2. And this is 3. Okay. Then this is positive infinity. And the intervals here are going to be in between the critical points. So I'm just going to design the intervals here. So this is basically one of the intervals, -infinity and -4. So it's not inclusive. Infinity can't be inclusive anyways because there is no number infinity. It's a continuum. But it's not going to include -4 because this is basically going to give us 0 in the expression. Now, the other interval here is between -4 and 2. So in between the critical points, this is another interval that we're going to be looking at. We also have an interval between 2 and 3, and we also have an interval between 3 and positive infinity. And the rule of thumb is that you're always going to have one more extra interval than critical points, right? So now we have 4 intervals, and after you create your intervals, the third step here is designing a table of intervals to test which of these intervals, which values of x will cause the expression to be less than 0. To do that, I'm just going to design a table of values of intervals. Okay, x belongs to, and then we're going to basically put those intervals in, so -infinity, -4. So place the intervals on top here, -4 and 2. We'll also have 2 and 3, and we'll also have 3 and positive infinity. Okay, so after you put the intervals on top, on the top row, then what I'm going to do here is I'm going to put my factors on this column here. Okay, so my factors, and you do have to include the -2, so I'm just going to include it with -2 and x plus 4. And you can put this in any order because multiplication is commutative. What that means is 3 times 4 is the same as 4 times 3. You can basically switch around the order. The other factor here is x minus 3, and we also have x minus 2 squared. Okay. Collectively, I'm going to call this guy f of x, which we said that f of x is this combined expression here. And then we want to test the signs. Now within each interval, I'm going to find a certain value of x. So that's why I wrote down x belongs to each of these values within the interval. So between -infinity and -4, I'm going to let x equal -5. If I let x equal -5, I'm going to apply this value to all of my factors in this column. So when x is equal to -5, we get -5 plus 4, which is -1, times -2, which is positive 2. So the sign here is positive. We just have to look at the sign. We don't have to calculate it. -5 in here gives us -5 minus 3, which is -8, so that's a negative. -5 into this factor. Now this factor will always create positive outputs because of the fact that even if you have a negative squared, you always get positive. So I'm just going to write positive across the board. So we really only have to look at these two factors. And you don't actually have to write this in your interval table, but it's good to kind of understand it. And then between this interval, let's say x is equal to, okay, let's test out the interval between -4 and 2. So let's say x is equal to 0. So then this is going to basically be 0 plus 4, which is positive 4, times -2 is -8. 0 minus 3 is -3. And then 2 negatives and a positive give us a positive, right? So what you can do at the end of this is you can multiply all the factors to get the overall sign of f of x. So the positive times negative is going to give you a negative, right? And whenever you see a negative value for f of x, we know that this is less than 0. So this is one of our solutions, right? Here we have a positive value, so this tells us a positive value means it's greater or equal to 0. So this is not a solution. I should get rid of that arrow. Okay, it's not a solution. Between the interval of 2 and 3, I'm going to let x equal 2.5. If x is equal to 2.5, if 2.5 plus 4, which is like 6.5 times negative 2, you can understand that that's a negative value. 2.5 minus 3, that's a negative value. This guy will always be positive, so the two negatives will give you a positive, so this is a positive, so this is greater or equal to 0, right? And then between that, we'll also take a look at, oh shoot, negative, yeah, that's negative, sorry. Anyways, let's take a look at the last point here, so 3 and positive infinity, so the last interval, x is equal to 4. So if I let x equal 4, then this is 8 times negative 2, which is negative 16, so this is negative. 4 minus 3, which is positive 1, and then this is negative. Right, so this is less than 0. So our two solutions here that are less than 0, where the inequality is less than 0 when it's negative, therefore x can belong to negative infinity and negative 4, but as well as 3 and positive infinity. So we use this symbol union to mean or, so it can be in this interval or this interval. Okay, and this is how we solve our inequality. Okay, solve the inequality x cubed minus 2x squared minus 5x plus 6 is less than 0. To solve this inequality, the first thing I want to do is factor this fully. I'm going to call this expression f of x, right? And if f of x is equal to x cubed minus 2x squared minus 5x plus 6, I'm going to factor this by using the remainder theorem. So if you're looking at the remainder theorem to factor out a cubic expression, what you need to be looking at is the integral 0 theorem, where you can actually look at some potential factors. And to find potential factors, you need to look at plus minus the potential factors of the constant, which in this case is 6. So it's 1, 2, 3, and 6. These are factors of 6, divided by the potential factors of the leading coefficient. In this case, there's a 1, so it's just plus minus 1. So some of our potential factors here include plus minus 1, 2, 3, and 6. Now they're potential because of the fact that they don't all work, right? So we just have to kind of guess and check. I'm going to do f of 1 first. If I do f of 1, you get 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6, which is basically 0. So this actually tells us that x minus 1, according to the factor theorem, is a factor. Now, because we know one of the factors, to find the rest of the factors, we need to use either long division or synthetic division. I'm just going to be using synthetic here. So there's the 1 here, and then we do x cubed, x squared, x to the power 1, x to the power 0, right? And you write down your coefficients. So this is like a 1, this is a negative 2, this is a negative 5, and this is a 6. And bring down the 1 here, and you get a 1, and then you multiply this out. So just memorize the procedure for this. You have negative 2 plus 1, which is negative 1. Then you do 1 times negative 1, which is negative 1, negative 5, plus negative 6 is plus negative 1 is negative 6, and then 1 times negative 6 is negative 6. Okay, then you add these two together, you get 0. So this guy here is our quotient, and the quotient should be 1 degree less than the dividend, which is basically your original expression, right? X to the power 1, x to the power 0, this is your remainder. So your quotient here should be x squared minus x minus 6. So your factored expression for the time being is x minus 1 times x squared minus x minus 6. Then what you can do here is you can factor out the quadratic. So if you do factor this out, you want two numbers to add up to negative 1, then multiply negative 6. So you can try negative 3x plus 2x minus 6, and then you factor this out. You can then factor this by grouping, and you get x plus 2 times x minus 3. Okay, so this is our fully factored expression, x minus 1 times x plus 2 times x minus 3. And instead of writing this polynomial expression, I'm going to be using this. So now, instead of writing this as my inequality, I'm going to rewrite this as x minus 1 times x plus 2 times x minus 3 is less than 0. Now at this point, what you want to do is you want to find some critical numbers, right? So the critical numbers here, my critical numbers here are going to be 1, negative 2, and 3. Okay, so you have 1, negative 2, and 3. And in this case, using your critical numbers, I want to figure out my intervals. So to find the intervals, it'll help to design a number line. And because it's less than 0, it's not inclusive of these points because this will equal 0. Then we're going to use open circles to not include the values. So you have negative 2, you have 1 here, and you have 3 here, positive infinity, negative infinity. And between the critical points, I can figure out intervals. So I'm just going to show the intervals out in yellow. So the intervals here is negative infinity and negative 2. You're going to notice that we're going to be using round brackets because of the fact that it's not inclusive of any of those two limits, the upper and lower limits. You have negative 2 and 1. You also have 1 and 3. And you also have 3 and positive infinity. Okay, so those are our 4 intervals, and after you have your 4 intervals, then you want to create your interval table. So I'm just going to erase this to make some space. And for designing our interval table, what you want to do here is place your intervals on top. So this is basically negative, infinity, and negative 2, and it's good to kind of order them out from lowest to highest. Negative 2 and 1. Then you have 1 and 3, and you also have 3 and positive infinity. Then what you want to do is you want to include your factors in these rows. So your factors include x minus 1, x plus 2, and x minus 3. And in this case, let's call this guy f of x, and we're looking for any intervals that are less than 0, so it's negative. And these are some values x can take on from these intervals. So between negative infinity and negative 2, I'm just going to pick a value. So let's say x is equal to negative 3. So if x is equal to negative 3, then this is negative. So you have negative 3 minus 1, which is negative 4. Negative 3 plus 2 is negative 1. Negative 3 minus 3 is negative 6. And then these 3 values will give us a negative, right? So this is actually less than 0. Between negative 2 and 1, I'm going to let x equal 0. And if x is 0, then this is negative, and this is positive, and this is negative. So you're going to get positive here. And then this is basically greater or equal to 0. Between 1 and 3, I'm going to say x is equal to 2. If x is equal to 2, this is positive, and this is negative. So this is going to give you a negative. It's less than 0. And then between 3 and positive infinity, x is equal to 5. And you can pick any number between this interval. In this case, you get 5 minus 1, which is positive 4, 5 plus 2, which is positive 7, and 5 minus 3, which is positive 2. And this is going to give you a positive, so this is greater or equal to 0. So our two solutions here should be this guy and this. Okay, so both of these intervals will give you a negative value, so therefore x can belong to negative infinity and negative 2 union 1 and 3. Okay, so any values from these two intervals will actually satisfy this inequality. Alright, let's solve for the inequality 8x cubed minus 10x squared minus 17x plus 10 is greater than 0 by factoring fully. So if we wanted to solve for this inequality, first what we need to do is we need to take this polynomial expression and convert it into factored form. Alright, so in order to convert it into factored form, we need to fully factor this inequality, right? So in order to fully factor this inequality, you can notice that this is a degree of 3, right? So it is a polynomial function, cubic polynomial function. So what we need to do is figure out one of the roots, and then we can do long division or synthetic division to find its quadratic quotient. And after that, we can just kind of factor out the quadratic quotient. So I'm just going to show you guys this. Let's say that this expression here is f of x. And in this case, f of x is equal to 8x cubed minus 10x squared minus 17x plus 10. What I'm going to do is I'm going to do the integral zero theorem and figure out some potential factors that may exist for this expression, right? So I'm going to use IZT to abbreviate integral zero theorem. And the integral zero theorem states that our potential factors can be basically factors plus minus the factors of the constant over plus minus the factors of the leading coefficient. Okay, so constant over the leading coefficient. So in this case, our potential factors here are factors of a constant here plus minus factors of 10, right? Because our constant here is positive 10. So we're doing 1, 2, 5, and 10. And factors of our leading coefficient plus minus 1. We're basically looking at this 8 here. 1, 2, 4, and 8. Okay, so our sum of our potential factors, if you divide this, you can have plus minus 1, 1/2, 1/4, right, 1/8, 2, 1/2, 1/4, so we have that again, 5 over 2, which is 1.5, 5 over 4, which is 1.25, right, 10 over 4. So this doesn't really it just gives us an idea, really, of what can potentially exist, right, and so forth. So plus and minus of these values. Let's test f of 1 first. Okay, so f of 1 here, 8 times 1 cubed minus 10 times 1 squared minus 17 times 1 plus 10. You can see that, right, this is like negative 8, negative 17 plus 10, so it's not equal to 0. We're trying to look for a remainder of 0, so that would tell us it's a factor. So f of negative 1 also, and you can keep testing this, does not equal 0, right? So I'm just going to cut to the chase here. And after trial and error, you can find that f of 2 will give you 0. Okay, so you can punch this in, right? So it will take some trial and error associated with this. So f of 2, we find out that f of 2 is a factor. Once you find out that f of 2 is a factor, what you want to do is you want to find out the remaining factors. So what I'm going to do is I'm going to do synthetic division. Okay, so if I'm doing synthetic division, I'm just going to do it out here. Okay, so I'm going to put out 2, right? So if f of 2 gives you a remainder of 0, then x minus 2 is a factor. And this is according to the factor theorem. Okay, so we can take out a 2 here, and I'm going to write down x cubed, x squared, x to the power 1, x to the power 0. X cubed term here is 8. X squared term is negative 10. X to the power 1 is negative 17. X to the power 0 is 10. What I'm going to do is bring down the 8 and you can multiply it, so you get 2 times 8, which is 16. I'm going to add these two together, so negative 10 plus 16 is 6. 2 times 6 is 12. Negative 17 plus 12 is negative 5. And then 2 times negative 5 here is negative 10, so this adds up to 0. Okay, so our quotient is going to have the terms x squared, x to the power 1, x to the power 0, and a remainder. So our quotient here should be 8x squared plus 6x minus 5. Okay, so this is where your quotient is, and you're going to also multiply. We know that the x minus 2 is already a factor, so this is basically our fully factored state. Now what you want to do here is you want to factor this guy out, right? 8x squared plus 6x minus 5. You want two numbers that multiply to negative 40 that add up to 6. Well, we could do 10 and negative 4, right? So 8x squared plus 10x minus 4x minus 5. I'm just kind of factoring out this inside term here. And I'm going to factor out a 2x. So you get 4x plus 5 minus 1. You get 4x plus 5. And if I factor this out, you get 2x minus 1 times 4x plus 5. And collectively, this is going to be times x minus 2. Okay, so this is your fully factored state, right? And if we, basically this expression and this expression are equivalent, and we're trying to solve for it when it's greater than 0, right? So if we want to solve for it when it's greater than 0, the idea here is that we need to figure out some of the potential intervals, right? So I'm just going to make some space up here. Just going to erase all of this out. Okay, so to create some of the potential intervals, what we're going to do here is we're going to, I'm just going to rewrite the expression. Okay, so we have 2x minus 1. So what we need to do now is we need to generate a number line to figure out the intervals. Okay, so to find the intervals, I'm going to create a number line, right? And values that'll make this equal to 0. I should do that first, actually. So let's figure out some values that make this equal to 0 so we can figure out our critical points. So our critical points, or critical numbers of x, are just points that we can use to figure out intervals, right? So we have to equate each factor equal to 0. So if I let 2x minus 1 equal 0, then 2x is equal to 1, right? X is equal to a half. So this is one of our critical numbers that we're going to plot, right? They're going to be non-inclusive points. Right? I'm going to let 4x plus 5 equals 0, 4x is equal to negative 5, x is equal to negative 5 over 4, right? So this is another critical number, and x can be equal to 2. So using these points, what I'm going to do is I'm going to design a number line, right? So if I design a number line, I do that up here, right? The points I'm going to plot here, let's say that this is 0, so this is like negative 5 over 4. I'm not doing, there's no arbitrary, there's just like an arbitrary scale, 1/2, and then this is like 2, okay? And this is negative infinity, this is positive infinity. So the intervals, we have 3 critical numbers, so we should have one more interval than critical numbers. So one of our intervals here is negative infinity, negative 5 over 4, right? So it's between these two. The other interval here is negative 5 over 4 and 1/2. And you can notice I'm using the round brackets because these are not inclusive. The other interval here is 1/2 and 2. The other interval here is 2 and positive infinity. Okay, so we have 4 intervals. Now what we're going to do here is we're going to design an interval table to figure out which interval will make our expression greater than 0. Okay, so what I'm going to do is I'm going to place my intervals on the top row here, like up here. Okay, so we have the interval negative infinity and negative 5 over 4. Right, we'll also have the interval negative 5 over 4 and 1/2. We'll also have the interval 1/2 and 2. And we'll also have the interval 2 and positive infinity. Okay, so beyond that, and these are just values x can take on within the intervals. And then what we're going to do is we're going to place our factors in these rows. Okay, in the last row here, I'm going to call this f of x to talk about my collective function. So all of this is my collective function f of x. And here I'm going to place my factors. So one of your factors is 2x minus 1. The other factor is 4x plus 5. And the other factor here is x minus 2. So what we're going to do is within each interval, we're going to test a point. So I'm going to let x equal negative 2 in this interval. And then you get negative 2 times 2, which is negative 4 minus 1, which is negative 5. So it's negative 2 times 4, which is negative 8, plus 5 is negative 3, so it's negative, and then negative 2 minus 2 is negative, so this is going to give you a collective negative, right? Between this point, I'm going to say x is equal to 0, so if you plug this in, this is negative, positive, negative, and that's positive, right? Between these points, I'm going to say x is equal to 1, so then that's going to give us positive, positive, negative, so this is negative, and then between this, x is equal to 3, so you get positive, 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 and then this is collectively positive, right? So we can notice here that the intervals that are collectively positive, this is less than 0, it's greater than 0, less than 0, greater than 0. So our answers are going to be this interval here, right between negative 5 over 4 and 1/2, as well as 2 and positive infinity, right? So therefore, I'm just going to write the answer there, but therefore x can belong to negative 5 over 4 and 1/2. It's going to erase this portion here. Union, as well as 2 and positive infinity. So values from these two intervals will satisfy the inequality. Okay, let's solve the inequality. Negative 2x cubed minus 6x squared plus 12x plus 16 is less than or equal to 0. First thing you actually want to do here to solve this inequality, we need to factor this fully. So to factor this fully, we know that this is a third degree polynomial. It's a cubic equation, and in order to do this, you have to actually employ remainder theorem and factor theorem. Okay, so to kind of do this, you're going to have to do a little bit of guess and check. What will help you out with this is the potential factors of our cubic expression, which is like negative 2x cubed minus 6x squared plus 12x plus 16. the potential factors is plus minus the factors of the constant, which are 1, 2, 4, 8, and 16. So they're factors of 16, over plus minus the factors of the leading coefficient, which are 1 and 2. Okay? And our potential factors, and we say they are potential because it doesn't mean that all of these are factors, but some of these or one of these will be a factor. So some of the potential factors can be 1, 2, 4, 8, and 16. And also 1/2, so 1 divided by 2, 2 divided by 2, which is 1, 4 divided by 2, which is 2, 8 divided by 2, which is 4, 16 divided by 2, which is 8. So we also have a half here. So you want to test some of these values out, right? So let's start with plus minus 1. I'm going to start with f of 1. So I'm going to pretend that this guy here is f of x, right? So what I'm going to do here is I'm going to do f of 1 here, and if I plug it in, I get negative 2, 1 cubed minus 6 times 1 squared plus 12 times 1 plus 16. And this is going to give me negative 2 minus 6 plus 12 plus 16. And you can actually notice here that this is negative 8 plus 12 plus 16. This is equal to 20. Okay, so this won't work, right? So f of 1 is equal to 20, right? So there is a remainder of 20. So we're still using remainder theorem. Let's do f of negative 1 just to test it. We have negative 2, negative 1 cubed minus 6, negative 1 squared plus 12 times negative 1 plus 16, right? You get positive 2 minus 6 minus 12 plus 16, and this actually gives you 0. So f of negative 1 gives you 0. So therefore, according to factor theorem, x plus 1 is a factor. Okay, so now that we know we have one of the factors, then what we want to do is we want to find the rest of the factors. So for this case, you can either use long division or synthetic division. As long as the factor is linear, as long as the divisor is linear, as in the degree is 1 on the divisor, then you can use synthetic division. So I'm going to use synthetic division for this. So when I'm doing synthetic division, let's do that here. I'm doing synthetic division. I'm going to write down my terms up top. This is x cubed, x squared, x to the power 1, x to the power 0. And then basically the value I plugged in to find my remainder, I'm going to use that on the outside. My coefficients here for the x cubed is negative 2. For x squared, it's negative 6. X to the power 1 is positive 12, and x to the power 0 is 16. Okay, so those are my coefficients. The first thing you want to do here is I'm going to bring down the leading coefficient, which is negative 2. So you bring down your leading coefficient. You multiply your leading coefficient with your k value, which is the negative 1. So when you multiply these two, you get positive 2. Then you add the coefficients of negative 6 plus 2, which is going to give you negative 4. Then you do negative 1 times negative 4, which is positive 4. Then you do 12 plus 4, which is 16. Then you do negative 1 times 16, which is negative 16. And when you add these two together, you get 0. Now, the quotient of synthetic division, because you're dividing a cube by a linear, or degree of 1, the quotient should have the terms x squared, x to the power 1, x to the power 0, and the remainder. Okay, so this quotient here is going to look like negative 2x squared plus 4x plus 16. Okay, so what our factored expression looks like so far is x plus 1 times negative 2x squared plus 4x plus 16. You can understand that this is a quadratic expression, and we can actually factor this further. So if we factor this further, I'm going to factor out a negative 2 here. So you get x squared minus 2x minus 8. And then you want to factor this quadratic expression. So for factoring this quadratic expression, we're factoring this by decomposition, two numbers that add up to negative 2 that multiply to negative 8, right? You could do 4 and 2. So negative 4 and positive 2. So I'm going to rewrite it this way and then factor this out. So you get x minus 4 plus 2, x minus 4, and then I'm just going to factor by grouping, right? So this is negative 2, x plus 2 times x minus 4. So our fully factored expression is x plus 1 times, I'm going to put the negative 2 on the outside, and you can write it in any order, x plus 1 times x plus 2 times x minus 4. Okay, so now that's our expression that's fully factored, except we're not done yet, right? Okay, so after we have the factored expression, I'm just going to make some space here. And next we want to figure out the intervals using this expression. So I'm going to rewrite my inequality as negative 2 x plus 1 times x plus 2 times x minus 4 is less than or equal to 0, right? And in this case, what you want to do is you want to find your critical points. Okay, so my critical points here, I'm just going to use a different color for this. My critical points here are going to be negative 1, negative 2, and 4. Okay. After you find your critical points, then what you want to do is you want to design your intervals, right? So design table of intervals. No, sorry, design, not table of intervals, design your number line to determine the intervals. Right, so we need to determine our intervals before we actually design our table of intervals. So to do that, I'm going to design my number line, which is this. And because it's less than or equal to 0, it's going to be inclusive of the critical points. So this is negative infinity. This is negative 2, negative 1, positive 4, and positive infinity. And then using my critical points, I can figure out what the intervals are. So this guy here is negative infinity and negative 2. This guy here is negative 2 and negative 1. This guy here is negative 1 and 4. And this guy here is 4 and positive infinity. So you can notice that we're using the square brackets because the points are inclusive, right? And after we design our number line and we create and we find our intervals, and you should see that there should be one more interval than critical points. If you have 3 critical points, you have 4 intervals. Then what we want to do is we want to design our interval table. So I'm just going to make some space here to design our interval table. Okay, so for designing our interval table, what we want to do is we want to place our intervals on the top. Okay, so we have 4 intervals that you want to place on top. So we have the negative infinity, negative 2, negative 2, negative 1, negative 1 and 4, and positive 4 and positive infinity. Okay, so we have our intervals on top. These x can belong to values within these intervals, and then we place our factors on these rows, right? Now the last row here is going to be our combined function f of x. Okay, so it's going to be basically the collection of all of the factors, right? So I'm going to place my factors. I'm going to include the negative 2x with the first factor, so negative 2x x times x plus 1. Then I have x plus 2 here, and then I also have x minus 4. Okay, and then I'm going to pick a value from each interval, so I'm just going to show that using a different color. Let's say between the interval of negative infinity and negative 2, I plug in x is equal to negative 3. If I plug in negative 3, you get negative 3 plus 1, which is negative 2, times negative 2, that's positive. Right, so you have to kind of test out one value for each column, and then you can figure out the signs of each interval. So in this case, for each factor. So in this case, x is equal to negative 3. You plug it into x here. Negative 3 plus 2 is negative 1, so that's a negative. Negative 3 for x. Minus 4 is negative 7, so that's negative. And then when you multiply all the 3 factors together, you get positive times negative, and that's going to give you positive. So this interval actually here is going to be greater than 0, right? But you want to look for values that are less than or equal to 0, right? So let's take a look at between negative 2 and negative 1. Let's say that x is equal to negative 1.5. If you plug in negative 1.5, you get 1.5, negative 1.5 plus 1, which is negative 0.5, times negative 2 is positive. When x is negative 1.5 plus 2, that's positive. Negative 1.5 minus 4 is going to give you a negative. Okay, so you have a negative times 2 positive, that's a negative. So this is going to be less than or equal to 0. It's less than or equal to 0 because if you include negative 2 or negative 1, it's equal to 0. And you keep doing this for the other 2 intervals. So for this guy, I'm going to pick x is equal to 0 because it's easy. 0 plus 1, positive 1 times negative 2 is negative. 0 plus 2 is positive 2, so it's positive. 0 minus 4 is negative 4, and then this adds up to a positive, right? Negative times positive. So this is greater than 0. And then for the last interval, from 4 to positive infinity, I'm going to let x equal 5. In this case, you get 5 plus 1, which is 6, times negative 2, which is negative 12, so it's negative. 5 plus 2 is 7, so it's positive, and 5 minus 4 is positive. So this is negative. So this is less than or equal to 0. And our two solutions are going to basically be this interval and this interval, right? And those are the cases where f of x will be less than 0. So therefore, x can belong to negative 2 and negative 1, as well as, or union, 4 and positive infinity. Okay, and if you pick any value from these two intervals, you actually see that this inequality will be true.